I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day.
Hello, good evening, Wondernauts. Allow me to call you that. Welcome to Wonderfest's presentation of Understanding Human Populations with Dr. Elizabeth Wrigley-Field. Thank you for being here. All right, Dr. Elizabeth Wrigley-Field is assistant professor at the University of Minnesota in the Department of Sociology and at the Minnesota Population Center. Dr. Wrigley-Field's adventures in higher education began at New York University with a bachelor's degree in sociology and a master's in philosophy. Then Elizabeth earned a master's degree and a PhD in sociology at the University of Wisconsin at Madison. I must, with Elizabeth's permission, mind you, explain the origin of her wonderfully baseball-friendly last name. Her mother is a Wrigley, and her father is a Field. But to avoid childhood teasing, they named her simply Elizabeth Field. However, at the ripe old age of 7, Elizabeth insisted her name become the hyphenated Wrigley-Field because, and I quote, being Wrigley-Field is clearly much cooler. I learned about Elizabeth through her remarkable chapter in a remarkable book. It's right here. It's called This Idea is Brilliant. It's one of the Edge series of books by editor John Brockman. And indeed, her chapter in this book, short chapter, is brilliant. Please welcome the brilliant and the very cool, in more than just name, Dr. Elizabeth Wrigley-Field.
Thank you so much for that welcome and for having me. I'm going to actually ask you to make my second account here a co-host, and I'll do the screen share from there. I'm really excited to be talking about length bias sampling because this topic is very near and dear to my heart. It's something that I was working on intensely for a few years, which ground to a halt in March of 2020. Because my other research life is I study infectious diseases, and in March of 2020, there came to be an infectious disease that I decided to study. So I've been really busy for the last couple of years doing something else, and it is such a treat for me to return to this topic that I particularly love. And I'm going to tell you about this work. And I want to start by presenting 3 puzzles. First, American fertility, so how many kids families had, fluctuated really dramatically in the early 20th century in the decades surrounding the Second World War. Parents made their smallest families during the Great Depression when they were economically squeezed. They made their largest families during the post-war baby boom. And yet, children born during the Great Depression came from larger families than those born during the baby boom. How can this be? Second, about half of the prisoners who are released in any given year in the United States are going to end up back in prison within 5 years. And yet, the proportion of prisoners who are ever released from prison, who will ever end up back at any point over their whole lifetime, is only a third, less than a half. How can this be? And finally, people whose cancers are caught early by a random screening often live longer than those whose cancers are detected later after they're symptomatic. And yet, those same random screenings might not save any lives. How can this be? So these are 3 seemingly very different puzzles. And here's the twist. These are all the same puzzle. The name of this puzzle is length biased sampling. It's also called size bias. It means seeing units in proportion to their size. And so what I'm going to do in this talk is I'm going to use that first family size puzzle to explain the idea And then I'm going to use those concepts to show what I think are some useful new ways to think about lifespans. And finally, I'm going to come back to the recidivism and cancer puzzles at the end, when we'll all have the tools to understand exactly why they're not as puzzling as they seem. So here's a hint to the family size puzzle. I'm just going to read it again with some emphasis. Parents created the smallest families during the 1930s and the largest families during the post-war 1940s. Yet children born during the 1930s came from larger families than those in the 1940s. And so the solution to this puzzle is going to be that parents' families and children's families are not actually the same, even though parents and children are in the same families. So what do I mean? Let's imagine these three families, and we're going to go around and ask one parent from each family, how many kids do you have? We get this data set, 1 kid, 3 kids, 8 kids. Their average is 4. That's our family sizes data set. But now we're going to take these same 3 families, and instead of asking a parent from each, we're going to ask the kids. And we're going to ask each kid, how many kids are in your family? And so what data set do we get now? Well, the family that has 1 kid, that 1 kid says, there's 1 kid in my family, that's me. And the family that has 3 kids, we have a kid who says there's 3 kids in my family, and then we have their sibling who says there's 3 kids in my family, and then their other sibling who says there's 3 kids in my family. And that 8-kid family, we have 8 reports of 8 kids. And of course, where there are households with no kids, we would never see that household at all. What average do we get? We add all this up, we divide it not by the 3 families, but by the 12 kids, and we get a little more than 6. So actually a much bigger average than the 4 kids. This is length bias. When we ask adults about their number of children, we get 1 response per kid, regardless of how many kids they have, even if the number is 0. If we ask children about the number of children in their family, we hear about it according to the number of kids that there are. And so the distribution we end up with is based on the distribution of squared values from the original distribution. And I decided not to really get into much math here, and but we can do more if you like. There's a few different characteristic expressions for a length biased relationship, but I decided it would be more fun to focus kind of bigger picture on the ideas. And so what I want to show you is something by a demographer, Sam Preston, who uses this math to develop one of my all-time favorite examples of a social implication of a mathematical population relationship. And so he draws out what I think is a really striking implication of this family sizes problem. He says, imagine if every kid from that 8-kid family had 8 kids of their own. And then those 8 kids have 8 kids of their own. You can see that you're going to end up with a huge population really fast. If everyone made a family that looks like the family that they themselves came from, the result would be a much faster population growth than we actually ever observe for any population, certainly for any human population. And so that tells us that people are not actually, on average, recreating the families that they came from. And Preston puts it like this. He says, the implications for population growth are obvious. Members of each generation must, on average, bear substantially fewer children than were born into their own family of orientation, merely to keep population fertility rates constant. A major intergenerational change at the individual level is required in order to maintain intergenerational stability at the aggregate level. And then he points out that that actually has all these social implications, because how many kids you have is wrapped up in all these other things, especially, he's writing this in 1973, especially your gender identity and the roles that women play. And so he says those who exhibit the most traditional behavior with respect to marriage and women's roles will always be overrepresented as parents of the next generation, and a perpetual disaffiliation from their model by offspring is required to avert an increase in traditionalism for the population as a whole. So in other words, for your population to just be pretty stable and not ballooning in this crazy way, structurally, you have to have it be the case that people's parents tended to have more kids. And for Preston, that meant more traditional lives. And the kids are constantly rebelling against that. And so what we think of as maybe a psychology of individual rebellion is actually also a population structure of kids rebelling against their parents. There are other implications of the family sizes problem that are important. If you don't pay attention to which distribution you're trying to describe, parents or children, you can really end up in a muddle. And so there's two wonderful sociologists, Shi Song and Rob Mayer, who point out that a lot of the research on intergenerational economic mobility is very muddled because you get a very different picture of social mobility if you start from a representative sample of parents' social origins and ask how their kids end up, versus if you start from a representative sample of kids and ask what their parents' social class was. And if you confuse the two and don't realize that these are separate questions, you don't actually know what you're finding out. And so at this point, you might be thinking that hopefully you think this is sort of interesting, but you might think this is also very specific. But what I want to argue is that length-biased sampling, this very family-size problem, deserves to be considered a fundamental concept at the core of understanding populations. That in a certain sense, all kinds of things look like family sizes. And so to convince you of this, I want to convince you to start with that lifespans cluster time the way that families cluster children. In other words, I want to convince you that lifespans are inherently length biased. And so the question that this middle part of the talk is going to focus on is, how long will the people who are currently alive be alive? How old will they be when they die? And so I'm asking this as a question about death, but actually you can think about that as a metaphor for any process that acts like death, in the sense that people are in one state, like the state of being alive, and then they leave that state, like dying. And so you could also turn this into a question about, of the people who are currently in prison, how long will they be in prison? Or of the people who currently have a disease, how long will they have it? Or of the people who are currently in a relationship, how long will that particular relationship last? So any kind of experience where the question that we care about is not about everyone who ever has this experience at any point, but about all the people who are experiencing this right now. What's going to happen to them? That's the kind of question that we are going to care about, but I'm going to talk about it as a question of lifespans. And to understand the structure of this problem, I'm just going to put it in this artificially simple context. It does not need to be in this context, but it makes our lives a little easier. And so for this setting, imagine a population that is constantly replacing itself. At any given moment, a certain number of people are born, and then the exact same number of people die. The ages at which people die never change. And also no one is migrating in, no one is migrating out. And so the only ways people enter are by being born or leave or by dying. We call this a stationary population. Most populations are not like this, although actually many historical demographers think that for most of human history, the human population was broadly like this before settled agriculture, when everything changed. But we're going to use this stationary population setting because it lets us think about population structure abstracted from all the complications that come with population growth. So at any given moment in this stationary setting, the life expectancy, which just means the average lifespan of this population, is the same. It's the same for people who are born at one time or the next time. And so now what I want to know, though, is not the average lifespan of the people who are born at any moment, that life expectancy that we're used to talking about and hearing about, but the average lifespan of the people alive at any moment. And the big idea here is that this average lifespan of the living is a length-biased life expectancy. So let me show you what that means. every population has some set of ages that people die at. So in this graph, what's going on, we're calling that age of death function the dx function. The x-axis here is age, and the y-axis is a percent of deaths that are happening at each age. And this picture happens to be a very typical distribution of ages for a lot of human populations, with lots of deaths happening to babies, and then a mass of deaths happening much later. This particular one happens to be based on Swedes who were born in 1917. We're going to imagine this as a stationary population based on Swedes born in 1917. And so we imagine that as new people are born and other people die, this function of ages at death never changes. Everyone who's born, so we call that a birth cohort, every birth cohort born at this moment or this moment or this cohort is going to have total lifespans that follow this distribution. And at any moment, the people who are dying are going to be dying according to this distribution of ages of death. But none of that is our question. We want to know the lifespans, not for the people who are born right now or die right now, but who are alive right now. And so we're going to organize this question by thinking about ages at death, starting with a very sad age at death, which is age 2. In this population, about 1% of the birth cohort, a little bit less than that, so we'll just call it 1%, dies at age 2. And we have a birth cohort of people in the population who are 0-year-olds. They were just born. And so 1% of them are going to die at age 2. And we also have a population of 1-year-olds. And if we go back to the original set of 1-year-olds when they were first born and ask, through your whole lives, how many of you will die at age 2? It's 1% of them. And if we go to the people who are 2-year-olds now, and we ask, among your 2-year-olds, how many of you are going to die at exact age 2? Well, if we go back to the original birth cohort, it's 1%. But if we're asking about the 2-year-olds who are alive right now, it's absolutely none of them, because they're alive right now and they're already 2. They're too old. And so we have just two ages in the current population, or 2 birth cohorts, the 0-year-olds and the 1-year-olds, who are still eligible to die by age 2. What about deaths at age 40? It's something like 1.5% of this distribution of each cohort is going to have its deaths at age 40. But how many of the cohorts who are currently alive can still have their deaths then? Well, it's 40 cohorts. It's everyone who hasn't reached age 40 yet. So it's a lot more than age 2. And that's the length bias. And so here's another way to see this. I'm going to show you demographers' favorite tool, which is called a Lexis diagram. And so the x-axis here is time, and the y-axis is age. And so a birth cohort looks like this. We start from people who are born at any moment. We follow them until they die, and they exist on this diagonal. And so if we define a cohort average age of death, or our cohort life expectancy, the constraint is everyone we're including started their lives at some exact moment, but there's no constraint on when they die. Or we could ask, what about the people who die at any moment? And these are the people in this horizontal line. So the constraint is everyone who gets included dies at one precise moment of time, but they could have been born any time before that. It's unconstrained. And now, what about the people who are alive right now? The shape we get is really different. It's this triangle. We have this kind of unholy amalgam of this cohort and this period shape. We select a moment in time, and then we follow people along their diagonal. And so that means that we're first selecting people on their lifespans, and then following. And the length bias we get, in effect, is because we're asking a period question about a cohort slice of the data. And so all of the people who died before this moment in time are selected out of the sample. The sample is systematically biased toward the higher ages at death. And so in place of our original dx function, which is there on the left, we get a distribution of deaths that looks like this. The original dx function is still there in yellow, but the green function on top of it is the length biased function, the distribution of ages of death of the people who are currently alive. And so you can see there's none of the deaths, almost none of the deaths to babies, because even though the people who were just born, as many as 6% of them are going to die before they live out the year, those people who are just born are a minuscule slice of the population that's currently alive. This is the length bias. And this has the implication that the lifespan of a living population at any moment is always larger than the life expectancy at that moment, in the same way that the distribution of family sizes according to the kids is always going to be more than the distribution according to the parents. And so what looks like a very different problem, families, how big is your family? How long will people who are alive live? At its core is the same selection mechanism. We see families, or we see lifespans in proportion to their size. So I started off telling you that this kind of length bias sampling is ubiquitous in studies of populations. And then I really only gave you these two examples. So let me give you a couple of more. It's likely that your friends have more friends than you do. You are a fixed reference point to yourself, right? So your own perspective is not selected on your number of friends. You just have the perspective that you have. But the fact that someone is your friend suggests that they are likely to have friends. Certainly they have at least one. You are their friend. And that suggests that they're the kind of person who is likely to have friends. And because of this mechanism, the distribution of friends is a length bias sample of the distribution of friends. And so if you think about why does Facebook make so many people miserable? Yes, there is an algorithm there that is designed perhaps to provoke emotions in you. But it's also a mathematical or a structural fact that most of the people you're friends with are more popular than you are. And most of the people who they're friends with are more popular still. It's not an illusion. It's just a network structure reality. And this network structure actually has some very cool epidemiological applications. One of them has to do with predicting flu outbreaks. So if you want to predict a flu outbreaks in a setting like a college campus, one thing you could do is take a randomly selected set of college students and follow them over the course of the semester and ask them about their symptoms and wait until you see people starting to seem like they have the flu and then say, it looks like we have an outbreak. This is a really inefficient way to capture flu outbreaks. What Nicholas Christakis and James Fowler figured out is that there's a much more efficient way to do it that's not very hard, which is first sample a bunch of college students and ask them to list their friends. Then sample the people who were listed as friends and ask them about their flu symptoms and monitor those sets of friends. And because those people are central to social networks, they're the people who have friends, they're also going to be central to epidemics that spread socially, like the flu, because they have a lot of friends. There's a cool kind of story about this flu prediction, which is that Christakis and Fowler published this in 2010 to some fanfare. They were hoping that this was going to become the new way that people predict the flu. And then it just so happened that in that same year, Google searches of flu symptoms predicted flu outbreaks incredibly well. And so even though Christakis and Fowler had given us this more efficient, tidy way to predict flu outbreaks than just following college students and getting their symptoms, Google flu searches seemed even tidier and even more efficient, although actually in subsequent years, they haven't always worked as well as they did that first time. There is another that closely related implication, epidemiological application of this length bias, and it has to do with COVID contact tracing. So one of the notable things about COVID as a disease is that it's highly over-dispersed. And what that means is that the number of people that each infected person goes on to infect themselves is much more variable than average. So we're now very familiar with this idea of the number of people that each infected person will go on to infect. When we average that number, that's the R naught that everyone has now heard a lot about during the COVID pandemic. Is R naught more than one? The pandemic is the virus is spreading. Is it less than one? The virus is falling back. That's good. But that average can be very uniformly spread over people, or it can be very variably spread. And COVID is over dispersed. It's very variable. Now, the way that most contact tracing works is it's called forward contact tracing. And it's that we take someone who's just come down with COVID and we ask them, well, who are the people who you've seen since you started to be sick? And those are the people who you might have infected. We're then going to get in touch with them and say, hey, you might have gotten COVID. You should take a test. Who might you have interacted with? This is forward contact tracing because it starts from one index case and moves forward in time. But in the case of a disease like COVID, where most people don't infect anyone, but a few people are going to infect a lot of people, this kind of forward contact tracing is wildly inefficient, and it very quickly overwhelms the somewhat meager resources of health systems. There is a good alternative, though, that takes advantage of this network structure, and it starts with backward contact tracing. So we take a newly infected person, and instead of trying to figure out who might they have infected, we go backward and ask, who might have infected them? And then once we've done that backward link, we ask of the person who might have infected them, okay, well, who might they have infected? So we go forward, but not from the original index case, but from the people who infected them. In effect, we're finding the friends of friends. And the reason why this works is that it's taking advantage of the length bias. It is identifying the cases who are likely to be the super spreaders. And so this article, for example, found that backward tracing would identify a case that on average generated 3 to 10 times the number of infections as just a randomly infected case was. So that one backward link makes the contact tracing 3 to 10 times more effective. Other examples are outside of the context of epidemiology. This book, Marked, is one of the most famous works of sociology of all time, and justly so. It's a wonderful book. And in this book, Diva Pager analyzes the consequences of having a criminal record for employment and her kind of headline findings. So she sends actors, Black and white actors, to go apply for jobs with fictitious resumes. And the headline finding is that white applicants with a criminal record were more likely to get called back for a job than Black applicants who had no criminal record at all. So it's a great book. And there's one part of it, though, that I'm going to tell you I think is absolutely wrong. And it's that in an effort to show that employers' fears of hiring people with a criminal record are misplaced, she does this study, this survey of Milwaukee employers, and she finds that of those who currently employ felons, 92% of them think that felons are good workers. But the population that her question is really about is not employers who currently employ felons. It should be employers who've ever employed a felon, right? And so if you imagine that the duration of employing a felon or your chance of employing a felon over time is proportional to whether you find felons to be a good workers, then that 92% is a length biased average. And this is really an incidence and prevalence problem. It's that kind of lifespan problem in disguise, where we've traded from the people who are ever born to the people who are alive right now. And that brings me back to that recidivism problem that we started with, where I said half of the prisoners who are released each year from prison return to prison within 5 years, but only 1/3 of prisoners ever return at all. So how could that be? The solution is that prisoners are different from each other. Some of them will cycle in and out of prison repeatedly. Others will never return. And so when we look at released prisoners at a single moment in time, or even those leaving in a short interval, like a year, the ones who we're seeing are disproportionately the ones who leave prison most often, who are also the ones who enter prison the most often. We're seeing the repeat offenders. And that's how we can end up with the people leaving in a year being actually vastly more likely to return to prison than the people who ever leave at all. And this brings us to our last example, the cancer screening. So we randomly assign people to cancer screenings. We find that the group whose cancer was identified through the screening lives with their cancer longer before they die. So they have a longer lifespan after that than the people who weren't screened. It sounds like the screenings really work. And yet I'm telling you that the screenings might not be saving any lives. So what could be going on? There's actually two different issues here, and we're going to imagine them with the same simple picture. So we're going to illustrate these by imagining everyone's disease follows the same progression, where they start out healthy, which we're calling unsymptomatic and undetectable cancer, which is a fancier way of saying you don't have cancer. And then you move into this status of being detectably sick, but not yet showing any symptoms. And then you move into the status of being symptomatic before eventual death. And we're going to imagine that everyone's cancer follows the same progression, which is actually a very reasonable thing to imagine. And both of the problems with this cancer screening example turn on the fact that where screenings identify cancer is in this intermediate stage of the unsymptomatic and detectable. The cancers are advanced enough to be detectable, but they're not yet symptomatic, because if they were symptomatic, you would go to the doctor and get a diagnosis anyway. And so it's this kind of sweet spot of, if we do a screening, we find your cancer, but you wouldn't have found it any other way, that we pick up. And so the first problem is what's called lead time bias. And it's a very simple problem. The screenings catch cancer at an earlier stage. If we didn't screen you, you wouldn't go to the doctor until you were symptomatic. And so if we're measuring the time since diagnosis, the screened people are going to look better because their diagnosis is farther back from their death. The cancer was caught earlier. Even if the screening didn't actually add any lifespan, we're just starting the clock sooner. This problem is pretty easy to deal with. So let's say once we know that this is the problem we need to deal with, we can estimate when the people who are screened might have been diagnosed if we hadn't screened them. Or we can look at what age they die at instead of how long it's been since their diagnosis. So we can trade one clock that we selected the start time for another clock where the start time is independent of what we've done with the screening. So that's the lead time bias. We can handle it. But there is still a length biasing problem, and it has to do with heterogeneity, not so much of people, but heterogeneity of cancers. Tumors are differentially aggressive. Some of them develop much faster than others. And so when we do the screening and we pick up cancers in this stage of being unsymptomatic and detectable, what that really means is that we pick up cancers in proportion to the length of time that they spend in this unsymptomatic and detectable stage. And so if we make a key but reasonable assumption that the durations of these stages are associated, so the speed at which you move from being unsymptomatic and undetectable to being unsymptomatic and detectable to being symptomatic to being dead, that all of those stages are associated, meaning you either have just a generally fast moving cancer or a generally slow moving cancer. Then when we select cancers that spent a long time in their unsymptomatic and detectable stage, we're selecting the cancers that move slow. And then we ask, how long do people live with this cancer? And we find, oh, we found it in our screening and they live longer, not necessarily because the screening worked, but because what the screening can identify are the cancers that moved slow enough that they were there to be identified, but not so symptomatic that they were identified anyway. These problems are a multitude of substantive areas. So we've touched on epidemiology, we've touched on sociology and employment, we've looked at family sizes, we've looked at lifespans, but at their core, they share a common structure. And I believe that this structure is a core relationship underlying how categories nestle inside each other. Tumor inside person, inside family, inside population, that deserves to have a much greater place of prominence in the concepts that we use to organize the social world. So I will end there and invite you to share the applications that are meaningful for you.
Elizabeth, that was terrific. I'm looking forward to questions here. I must say, one of Wonderfest's programs that I described at the start was to present workshops for PhD students from UC Berkeley and Stanford in science communication. And I've had an opportunity to learn a lot about speaking in public. And I got to say, I don't think I've ever heard anybody speak so clearly, so coherently on what I think is a difficult subject. Thank you for that presentation.
That's so kind. Thank you.
Oh, boy.
I love this topic, so it's really fun to talk about.
No one's typed in the question in the chat. I'll pose a question, but I'm looking forward to seeing a hand raised or perhaps a typed question. It does seem like this challenge of length biased sampling would pop up just about everywhere. Is this knowledge widely dispersed? Do most people, statisticians of all sorts and sociologists around the world know about this?
Well, I'm going to say no, but it does depend who you're asking about. So this is a well-known branch of statistics. There's a lot of work. We understand the properties of length bias samples really well, but it's also knowledge that is very siloed. So I am a sociologist and I'm also a demographer. I've taken a really excessive number of quantitative methodology courses in my time, and I never learned this in any of them. And so actually the way that I came to this material was I was studying for my demography prelim exam and in grad school. And the nature of studying for this exam is I was looking at all different topics kind of all jumbled together as I was frantically cramming. And so I read this paper on family sizes, and then not that much later, I was reading some very technical work about the average age in a stationary population. And I recognized that, and it was this formula that is just totally hard to grasp any intuition from. It made no sense. And then I recognized that actually where the formula was coming from is it was just the family size problem. And then with the divided in two, because if you want to know the average age of someone in the population, it's their average lifespan, but you see them halfway through it. And I realized, oh, the lifespans are clustering time the way that families cluster children. So I came to it sort of very much by mistake. I've never seen it in any textbook in either of my fields. And so I've become a bit of an evangelist for trying to tell people, hey, there's kind of a unifying structure to all these different problems that we do. And if we recognize it, we can actually make more headway on some of these problems because we can take insights from one application and import them to another place.
Yeah. Do you think John Brockman, the editor of this book that allowed me to describe you, how did you think he came to understand that you had this insight that, by the way, the subtitle of this book, I want to tell folks, is Lost, Overlooked, and Underappreciated Scientific Concepts Everyone Should Know? It seems like your topic, length bias sampling, was custom made for this book. How do you suppose Brockman came upon you and the idea?
So I think he asked me to write about anything or to propose any topic. And this is the one I thought right away, oh my God, I have an overlooked topic. It's length bias sampling. And that came because I had written something for that annual question series the year before, where I wrote something about translating between different levels of understanding a problem. And the kind of irony of that is that when I wrote that first essay, which I had a lot of fun doing, I wasn't thinking about length bias sampling at all, but I came to realize after I wrote the second one that in a way it was actually the same. They're very different essays, but it was actually kind of the same points. And I think that does reflect that so many of the problems that we try to understand actually turn on shifting your perspective from, for example, an individual to a population, or an individual patient to the tumors inside the patient. And whenever we have these problems that involve this kind of shift of perspective, it's very likely that length bias is lurking there, leading us to have one perspective be weighted in a very different way than the other.
All right, thank you. Is it fair to assume that if among the Wondernauts here at this event, we have some aspiring sociologists or population experts, or perhaps they're the parents of such future experts, would you advise that along with perhaps studying philosophy, as you did, they would want to brush up on their math, that math skills are important to the study of modern sociology and populations?
Yeah, I mean, so I teach a statistics class for sociology majors, and it's very much a class to help students who have been intimidated by math realize that they can do math and it can give them some power. So I think math is incredibly helpful for understanding how populations work, but it is also something that in our social context in the United States that a lot of people have really been denied access to. And we have this kind of mythology that math is for white men and that it's not for women or students of color or first generation students. And so part of what I try to do in my teaching is make math something that everybody can kind of get the power of. And so you can be a sociologist and never do anything like this. You can be a sociologist who does brilliant work interviewing people. But how much cooler is it if you can do that brilliant work interviewing people, but also be able to think about the network structure of your interviews and what kind of analytical power does that bring to you?
It's almost as cool as being named Wrigley-Field.
Well, let's not go that far.
Okay. I want to thank everyone for being here, all you Wondernauts. It's great to see you here with your curiosity. I want to remind you that our next online event happens on January 10th. It's Never Home Alone with entomologist Dr. Bernard Lewis. That's online. And in person, our next event is the preceding day, January 9th. It's Going to the Stars. And by the way, this is quite literally a small fleet of robot craft are in the making, or at least in design, by the Breakthrough Projects. And the executive director of the Breakthrough Project, the former former leader of Ames Research Center, is Dr. Pete Wharton, and he'll be here. No, he'll be in Castro Valley telling us about that. So I want to offer you the suggestion of visiting wonderfest.org to learn about these events. But most of all, right now, please offer a big thank you to Wonderfest patrons and supporters, and most of all, to our great guest speaker, Dr. Elizabeth Wrigley-Field. How about some American Sign Language or audible applause if you want to unmute yourself? All right. Elizabeth, thank you so much.
Thank you so much.
All right. Good night, all. See you at the next Wonderfest event, I hope.